Van der Waals differential method. Van der Waals differential. What is the Van der Waals differential method? We have already discussed, in which A plus B will giving products. And how to determine the order of the reaction with respect to A, with respect to B, with respect to C, for which we are keeping one of the other two reactants as a constant, or according to Oswald's dilution law, we can have these B and C in large excess. Therefore, now the rate of the reaction depends upon the concentration of the A and B. Varying the concentration, we can determine this one. Or which we have given a data, time in various time, 0 time, some T1 time, T2 time. And what is the concentration? At this concentration, we have given C1, C2, and so on. From this, we have determined the rate constant using the equation R1 rate by R2 is equal to the K rate constant with respect to the A into the concentration of power 1, right? The concentration of A1, similarly divided by K2 power concentration of the A at the time 2 power n. Or we can simplify the equation, this K1, sorry, this is K1, this K1 and this K1 gets cancelled. You will get the final equation as A1 by A2 power n. Using this equation, we have worked out the problems. And using in this formula, we are going to work out 2 more formulas. And then we left with this Oswald's or Van der Waals dilution. Sorry, differential. Okay. And go for some other, some fast reaction kinetics problems. And take down this question, which is asked in the year 2016. If the rates of your reactions are R1 and R2, capital R1 and R2, at the concentration C1 and C2 of your reactant respectively, the order of the reaction N within bracket, assuming that the concentration of all other reactants and T, that is temperature, remains constant. Close the bracket. Assuming that the concentration of all other reactants and temperature remains constant. Close the bracket. With respect to that, reactant is given by N is equal to log of R1 minus log of R2 divided by log of C1 minus log of C2. This is the first option. Second option, you can give any number of options. I have given the various options A, B, C, and first answer we have given. The other answer you have manipulated is the numerator can be made a denominator and the denominator can be made as a numerator. Or you can change the terms either in the numerator or in the denominator. Therefore, what is number there? Denominator log C1 by C1 into log of C2 divided by log of R2 minus R1. And of these are 4 options, which one is correct one? Because we are keeping the concentration of the other reactant as constant. We have already worked out this one. In part way, we are working out the rate is equal to the rate constant into the constant Pn. For first concentration, let it be R1 K1 and A1 power n. For the second two, at the same temperature, therefore K1 is remaining constant, A2 power n. And then keeping what given by adding this equation, final equation, this one, we are generally using this equation for calculation purpose. Use the same equation and derive the value for n. Here it is given in terms of log. Therefore, take log on both sides. You will get log of R1 minus R2 log R1 equal to log of A1 by A2 power n, or simplify this, log of R1 minus log of R2 is equal to n into log of A by A1 can be written as log of A1 minus R. Here instead here it is given as concentration C. Therefore, we put it in the form C1 minus log of C2. Therefore, now what is the value of n? N is equal to, which is the correct option here? Tell me the option.
Option A, sir.
Option A. This is asked in the year 2016. This is just a derivation. And now I am giving one more problem in this section, and I will close these kinetics problems. Take down, this is asked in the year 2013. Take down the question. In the reaction between nitric oxide and hydrogen, the following data are obtained. And take down the data. The experiment 1, first experiment. Here, reaction between nitrogen and hydrogen. Therefore, here to obtain the order with respect to, you have to keep any one of them as a constant. Experiment 1, the pressure of hydrogen is a constant. Pressure of hydrogen is constant. And the data obtained are pressure of nitric oxide. Here it is going to be changed in milligram mercury. And what is the rate of pressure of nitric oxide? Nitric oxide or nitrogen? Nitric oxide, sorry. And the answer given is, the pressure of the nitric oxide is 359 millimeter of mercury at time. The rate of the reaction is 1.5 and 300. The rate of the reaction is 1.03 at 152 millimeter of mercury. The rate of the reaction is 0.25. This is the first data. அடுத்தது experiment 2. In the experiment 2, you are keeping the other reactances constant, which is to be kept constant. The pressure of nitric oxide is kept constant, which is very. The pressure of hydrogen is very. The pressure of hydrogen is very. It is in millimeter of mercury. And here the decrease in the constant in the pressure of hydrogen with respect to time. The rate is directly given. That is given as 289 millimeter of mercury. At that time the rate is 1.6. 205, the rate is found to be 1.1. And 147. 147. The rate is 0.9989. Question is, the orders with respect to hydrogen and nitric oxide. Order with respect to hydrogen and nitric oxide are option A. First order with respect to nitric oxide and second order with respect to hydrogen. And option B, second order with respect to nitric oxide. And you can tell me then another way, one first order with respect to hydrogen. C, first order with respect to nitric oxide. And third order with respect to hydrogen. Option D, second order with respect to nitric oxide and second order with respect to hydrogen. You can easily work it out. And which is to be taken first? Either the hydrogen can be, the order of the nitrogen can be taken, or either the hydrogen. Here order is directly given. You know the formula R1 by R2. That is first rate R1. This is rate R2. At that time, the concentration. Here concentration instead of concentration, you put the pressure to forward again. That's all. Here this is the pressure, that is at the rate is R1 is equal to pressure R at P2, the rate is R2. Just sufficient substitute, you find the N. Easily it will be, you can obtain the N. How to obtain the N? Already you know it. What about this data? It's a surplus data. You can make use of it, otherwise you can leave it. Similarly, these two data are sufficient. And this is a surplus data. Apply these two data and put the order with respective height and how to each one. Okay, then we will now enter into the topics. The topic we have to discuss this morning, problems in the fast reaction kinetics. Fast reaction kinetics. What are the fast reactions? What are the techniques adopted fast reaction? First we will see the techniques adopted in the fast reaction to follow the fast reactions. The first is flash photolysis. Flash photolysis. From the name itself, you know that this fast reaction is initiated by means of photoradiations. Therefore, there are problems with respect to flash photolysis. We can see chemical kinetics of photochemical reactions. Therefore, we are not going to discuss any problem now because the photochemical reaction kinetics is separate one. And second is that the stop flow methods. Or flow methods, I will start continuous flow and stop the flow method will be there. Stop the flow. And third is the relaxation method. Relaxation method. And we are going to see the relaxation method and the flow methods. We are going to see only the continuous, not the stop flow method. Therefore, only in that person we are going to see problems in the relaxation method and in the continuous flow methods. So far, I think no question is asked in this SIR examination. This year, my question may be appearing from this section. So, we'll first see the relaxation technique to which one this can be applied. Relaxation technique. What do you mean by relaxation? What are the formula available? You will see it will be simple one. Relaxation technique. And the relaxation technique is applicable when the reaction is to be in equilibrium. This is the should be present in the equilibrium. For example, A is in equilibrium with B, let us assume a simple first order kinetics, and the forward reaction is also following first order kinetics. Backward reaction is also following the first order kinetics. The rate constant for the forward reaction is K1, and the rate constant for the backward reaction we normally write it as K minus 1 or K inverse 1. Or in some book it is represented as K2. Equilibrium is attached and the equilibrium constant K, capital K is given by K1 by K inverse 1. Or K for the rate constant for the backward reaction. Whenever a system is attaining this equilibrium, one technique is adopted. You apply some disturbance to the system at the equilibrium. Disturbance in quantum mechanics, it is called perturbation. You apply some perturbation to this one. Whenever perturbation is applied, the equilibrium is destroyed and the system would be taken to in some other state. In that state, once again it attains an equilibrium. That you know this is a concept of this one. And how you disturb this system? What are the methods available? Generally, whenever equilibrium reaction, the equilibrium can be disturbed by applying whatever may be the nature of A, nature of B, or the products or reactant. The easiest way to apply a disturbance to A is by change in the temperature, sudden change. It's not a gradual change. Here, the disturbance should be given all on a sudden, not a gradual, sudden change in the temperature. Suppose, let us assume these reactants are taking place, a reaction is taking place at 25 degrees centigrade. Suddenly increase the temperature to 150 degrees. It is now the system is no longer at disturbance. And now, if the temperature is suddenly changed, and that method we call it as the temperature jump method, or shortly it is called T-jump method. Or some we can also change it if the A is a gaseous, B is a gaseous nature, then you can, in addition to the temperature jump, you can give a pressure jump. It is T-jump technique. Or if A and B are ionic, there may be, they are accessible for the conductivity or the electric field one. You can suddenly change the electric field method. It is called the electric field jump. The electric field jump. Or system is susceptible for the pH change. You can apply pH jump technique. That can be applied depending on the nature of the reactant and the product. But a common jump applied to whatever may be the system present is the pH jump technique. And whenever, I already told you that whenever you change the temperature, the equilibrium is destroyed and the system is taken to be some other state. And in that state, the equilibrium is once again reformed. Is once again reformed. And there will be some time required for the system to attain the equilibrium. That time taken, we call it as relaxation time. That is time taken for the system to become equilibrium in the another state is called relaxation time. It is normally represented by tau, represented by the tau. And there is for the relaxation time, there is a constant called relaxation constant. Relaxation constant represented by small kr. And the relaxation constant, this k we call this the equilibrium constant. What is the relationship between the rate constant for the forward reaction and rate constant for the backward reaction? It is nothing but k is equal to k divided by the rate constant for the forward reaction divided by the rate constant of the backward reaction. For relaxation constant can be obtained from this K1 and K inverse such that the relaxation constant is given by rate constant for the forward reaction and rate constant for the backward reaction. This is the relaxation constant. For the system. For the system is A only one reaction and there is B another only one product, and they are following the first order kinetics. Therefore, for this is the relaxation kinetics, relaxation constant relationship between the forward rate constant and the backward reaction. Just is some of this. Suppose now your reaction is such that it is in this way. A with the inverse arrow giving B plus C. B plus C. Here, the rate constant, let us forward reaction as 1 and the rate constant for the backward reaction is A2. For this, the forward reaction is a first order kinetic, whereas backward reaction is a second order kinetic. Your order is changed. For this, the Kr is not the sum of K1 and K2. Some other term is also involved. Whatever involved, that can be written as Kr is equal to the forward reaction into one concentration term, therefore beta H plus the backward action K2. We have written this is the situation. This is the situation. Now we have written this one. But here two concentration terms there. K2 in the concentration of B, K2 in the concentration of C should be introduced. Therefore, you are getting K2 into concentration of B plus C, two concentration terms. Therefore, here you have to put 2K2 and Xe. What is Xe? Xe is called equilibrium concentration of B or C, any one, because they are stoichiometry is 1:1. If C is Xe mole concentration is present at equilibrium and B is also Xe mole. Suppose this is called the relaxation constant. We can obtain the relaxation constant like this. Suppose it is in the other way, A plus B giving K1 by K2 M plus C. Now what is the relaxation constant? It is K1 in forward reaction. The second, the backward reaction is a first order. Therefore, K1 into the concentration of A plus the concentration of E. Here we have written like this, but the concentration is given as the equilibrium concentration. Here, what is the concentration of A and B left at the equilibrium K1 plus K2 into the concentration. Only one term, not necessary it will be. When you are deriving this relationship, that will be gets cancelled. And this is the equation for the relaxation constant. Suppose you are given A giving 2B with the inverse. What is the relaxation constant? Let us assume K1 and K2. Kr is equal to. It is equivalent to this case B plus A, same question, K1 plus 2B can be written as B plus B and 2B and K2 concentration of B in concentration of B. XE equation similar to this equation. Therefore, you can easily write down the relaxation constant equation. After writing down the relaxation constant, there is a relationship between these two. What is the relationship between the relaxation time and relaxation constant? The relaxation time or the Kr, anything is, one is inverse to another, or 1 by tau is equal to Kr. But Kr is nothing but for this reaction, Kr is nothing but rate constant of the forward reaction and rate constant for the backward reaction. And here, the relaxation time can be determined by spectroscopic method or any convenient method. You can easily find out the relaxation time. Once you know the relaxation time, you can calculate the rate constant for the forward reaction and rate constant for the backward reaction. And now you are having three types of question. One is for A to giving A and B are in equilibrium with the first order with respect to forward reaction and first order with respect to backward reaction. And in this, A is the first order, forward reaction is first order, but backward reaction is a second order. In this type of reaction, the forward reaction is second order and backward reaction is K2. Depending upon the order of these reactions, we will be having different equation for the relaxation constant. These relaxation constants are are related to the relaxation time. The relaxation time can be determined by a suitable technique. Now we are going to see problems for this one. So far, one question is asked in the year 2016, I think so, based upon this, that is forward reaction, first order and backward reactions also. First order, for which relaxation time is given by this method. For this relaxation time is given by this method. And if relaxation constant, and then relaxation constant that can be correlated like this. Now you have obtained one equation to solve K1 and K inverse 1, and you are in need of another equation. There are only two unknowns can be solved. That can be done by using, if equilibrium constant of the reaction is known, you can do this one. Now you are having two simultaneous equations, making use of this on the equation to obtain K1 and K2. Now we are going to work out problems in this type of problems, one or two, and then the rest would be given as exercise. Take down the problem asked in the year 2016. The reaction A with the reversible arrow, K1 for the forward reaction and K inverse for the backward reaction, is first order in both directions. is first order in both directions. The forward and the backward rate constants are 4.2 the 10 power minus 4 per second. Why the unit per second is given? Because the forward reaction and backward reactions are first order. And the rate constant for the backward reaction is 1.04 into 10 power minus 3 per second. The relaxation time for this reaction, the relaxation time for these reactions, bracket by in second, in a temperature jump experiment is, option A, approximately 500 seconds, B, approximately 600 seconds, C, approximately 680 seconds, D, approximately 750 seconds, approximately 50 seconds. How to work out these problems is very easy now, provided if you understand the concept. So far we have discussed. Write down the given equation. The given equation is A giving E with the reversible arrow K1 and K inverse. Therefore, what is the relaxation time? Relaxation time is that is asked. Tau is asked. This is asked. Therefore, what is the relaxation constant? You should know the relaxation constant. It is given as it is equal to the rate constant for the forward reaction and rate constant for the backward reaction. Therefore, Kr is equal to sum of these two, 4.2 into 10 power minus 4 plus 1.04 into 10 power minus 3 equal to 1.46 into 10 power minus 3. Do you understand the summation? How I have added this, or do you want some more explanation for this? Shall I proceed?
Yes.
Hello. You know how this result is obtained, is not? How this result is obtained. Just to convert into 10 power minus 4 or 10 power minus 3, convert it. It is equal to 0.42 into 10 power minus 3. Therefore, 1.04 plus 0.42 is summation of 10 power minus 3. Therefore, 1 by tau is equal to, according to our rule, is equal to relaxation constant Kr, but relaxation constant is equal to 1.46 into 10 power minus 3. Therefore, tau is equal to 1 by 1.46 into 10 power minus 3. It can be written as 2 by 3 into 1000. Equal to 2000, nearly the value is 700. What is less than 700? Do you understand how I have converted this into this? Do you follow?
Yes, sir.
Do you follow? 1.5, treat it as 1.5, it is nothing but 3 by 2. I have converted this. 2000 divided by 3, this nearly 7. What is the correct answer for that? What's the correct answer? Correct answer?
C, sir.
C, sir.
C option. C is the correct option. Now I am going to give you another method. Here I am going to give here K1 and K and the forward and the backward reaction constants are given. You are asked to calculate the relaxation time. Now we are going to change the problem. Relaxation time should be given, and you are asked to calculate what is asked to be calculated. The forward reaction constant and backward reaction. Two unknowns are asked. Therefore, you are in need of one more data. What is the data for this? You have to give the equilibrium constant. Then only you can solve the problem. Otherwise, it is going to be difficult. In this way, I am going to give another equation. I want to take down this one. In a temperature jump experiment, the relaxation time for the simple first order bracket in both directions. Close the bracket and write down A with reversible arrow B is found to be 800 seconds. Here relaxation time is given. Calculate the rate constants for the forward and backward reactions. Rate constant for the forward and backward reactions. And you are in need of one more data, otherwise the problem cannot be solved. You can give the data only in terms of the summation of K1, the forward and the rate constant for the backward reaction. You can give the problem up to this. But individual determination, you are in need of one more data. That data is the equilibrium constant. Calculate if equilibrium constant of the reaction is 124. Option A, 1.25 into 10 power minus 4, 1 into 10 power minus 6. To B option 3 into 10 power minus 4, 2.4 into 10 power minus 6. C option 1.25 into 10 power minus 3, 1 into 10 power minus 5. D option 3 into 10 power minus 3, 1 into 10 power minus 5. First, we will apply the logic argument. Then we will, if that logic argument, if you are lucky enough, you will get the answer. Then we will go, otherwise, if the logic argument is the problem is not answered, then you go by the stepwise method. What is the logic argument? This is the rate constant for the forward reaction and rate constant for the backward reaction. And what is the K given? Equilibrium constant, it is 124. And just divide the forward by backward, 10 power minus 5. It is equivalent to 300. Definitely this is the answer. And if you find here, the answer is 125. It's not 1.25 into 10 power minus 3 divided by 1 into 10 power minus 5 equal to 125. This may be a one answer. Similarly, here find it out. 3 divided by 2.4. Here if you find it, 1.25 10 power minus 4 divided by 1 into 10 power minus, once again 125. Therefore, by the logic method, it is not possible to give the answer. Therefore, go by the regular method we are adopting. Write down the equation. A with giving B with the reversible equation. And the Kr for this reaction is K1 plus K2 inverse 1. And the time of relaxation 1 by tau is equal to K1 plus K minus 1. It is given as 800 equal to K1 plus K inverse. This is equal to 1.25 into 10 power minus 3 equal to K1 plus K minus 1. Okay, we have first to find out the one equation. There is another relation is necessary that is obtained from K. K is equal to forward reaction constant by cathode reaction constant. K equal to 124. Therefore, K1 is equal to 124 into K inverse 1. In the place of K1, substitute it here, you will get 124 K inverse plus K inverse equal to 125 K inverse. And K inverse is equal to 1.25 power minus 3 divided by 125 equal to 1 into 10 power minus 5. Therefore, this is the constant for this, which is present where here it is present. Therefore, the option is. And you can also find out the K1 value just multiply it with this. That is 124 into K1 is 1 into 10 power minus 5 equal 1.24 into 10 power minus 3. That is the answer. Thus you can easily obtain this one. Now I am going to give you 2 or 3 problems you have to work out in your code. Take down the problem. The relaxation time for the reaction A in equilibrium with B is 10 microseconds. Is 10 microseconds. The T is given as 10 microseconds. And the equilibrium constant is 1 into 10 power 3. What is the K1 and the K inverse 1? Options A 10 power 5, 10 power 2, B 10 power 4, 10 power 1, C 10 power 8, 10 power 5, D 10 power 6, 10 power 3. You can't apply the logic argument in all the cases. The K will be equal to 10 power 3. Therefore, you go just a procedure method and find out the correct answer. This is an exercise for you. Now take down the another equation, which is not at all asked so far in the CSR examination. Maybe expected this year. The relaxation time for the fast reaction. Ammonium hydroxide, decomposition of ionization of ammonium hydroxide as ammonium ion plus OH minus ion. This is the ionization pathway. And this is K1 and this is K inverse 1. This point, the relaxation time is 0.1 microsecond. 0.1 microsecond. The equilibrium concentration of ammonium ion, is 4.1 into 10 power minus 4 mole per dm cube, mole per dm cube. And the equilibrium constant is 1.8 into 10 power minus 5 mole per dm cube. Calculate K1 and K inverse 1. We just to find out, the options are not given, just to find out K1 and K2. Okay, we will go for another type of problem, take down the problem. For the dissociation of water, H2O with a reversible arrow, giving K1 and K2, H plus OH minus. The relaxation time is 40 microseconds. Ionic product of water is 10 power minus 14. Calculate the rate constants K1 and K2. Calculate the rate constants K1 and K2. This is a very, very important one. Here, ionic product of water is given. Now this problem is just like the last problem, ammonium hydroxide ionization. But there, the equilibrium concentration is directly given. Here the equilibrium concentration of the H plus ion and OH minus ion are not directly given. From the ionic product, you can calculate the equilibrium concentration. Xe is equal to 10 power minus 7. That's all you should write down this. And one more parameter is not given for this reaction. What is the parameter you are in need of it? You are asked to calculate K1 and K2. Whenever two constants are required, you are in need of two equations. One equation is the relaxation time, inverse of the relaxation time is the relaxation constant. For this reaction, you can calculate the relaxation constant Kr is equal to, already you know that equation Kr is equal to K1 plus 2K2 into Xe. You already know it. But that from this you can arrange the one equation for ready for solving for K1 and K2. But equilibrium constant for this reaction is required. This constant is not the equilibrium constant. It is the ionic product of H plus and OH minus. You have to find out the equilibrium constant for this one. How to find out the equilibrium constant for this? The equilibrium constant is equal to the concentration of H plus into the concentration of the OH minus divided by the concentration of water. What is, you know this? It is equal to 10 power minus 4 T divided by concentration of water. What is the concentration of water yesterday? Is over 55.5. You are now making use of this. You have to find out the equilibrium constant for this reaction. What is the flow system? Reactions in a flow system. What do you mean by flow system? So far we have discussed the chemical reaction kinetics in a static manner. Here the reactants or products are present in a constant result. But in industries, in the preparation of some products, you have studied kinetics. In that industry, the reactions are not in the place they are some continuously and how much are formed each time. And when you take the products complete conversion, that will change. And for flow system. Flow system, it is applicable in the industrial methods of preparation of compounds. Here the reactants are mixed and the reaction is going on. It is mixed together in a mixing tank. It's a mixing tank. From the mixing tank, it is going through a reaction chamber. At want length it should be there, and final product, majority of the reactant should be converted to products. Such a kinetics have to be used in industries. Here in the kinetic arrangement is taking place in the system which is closely undergoing moving. This we call as the flow system. The flow system, there is a two type of flow. One is called flat flow and another is called stirred flow. What is the flux flow? It is here. Here in this flux flow method, no stirring is allowed while the reactant is passing through the vessel, reactor vessel. It's called a reactor. For a stirred flow means here while passing through the reactor, the solutions are stirred together to or close contact with each other or intimate mixing, it is stirred. Here a different kinetics, here a different kinetics. We are going to see these kinetics although not this one because it calculation is somewhat lengthy. I think it will not be Therefore, we are going to see the flux flow method. In the flux flow method, after mixing, the mixed solutions are pumped into the reactors. The reactors of known volume is P, let us assume. The pumping speed or the flow of the reactants may be varied, or the flowing speed, let us assume, that it be U. It is a meter cube per second. We are measuring it. The volume of the reactor is given in meter cube. If in this rate, if the reactants are moving inside the reactor, what is that is called the residence time in the reactor. Resident time. What do you mean by resident time? The mixer, how long it will be present within the reactor. That is given by V by U. That is the volume to be grasped. What is the flowing rate? Flowing rate is given not in meter cube meter per second, volume in the meter cube. From this you can easily calculate the resident time is 1. And here there will be a detector at the entry point. At the entry of the mixer into the reaction chamber, entry point there will be a detector to detect what is the concentration of initial concentration. Then it is entering into the reactor. There is another detector at the exit of the reactor. And the detector is detecting what is the concentration of the reactants when the solution is going outside the reactor. In the entry point, let it be CI, and in the outer it will be CF. And it is given by the formula CF is equal to, for first order kinetics, I am giving it for a first order kinetics. And for the first order kinetics, the reaction, the equation in kinetic equation is concentration at the exit, CF is equal to the concentration at the entry level, CI, e power and K1. K1 is the rate constant for the first order kinetic by the resident time. Resident time is how long the mixture is present within the reactor. This is the resident time. If you compare the equation, this is the flow, this is the kinetics for the flow system. For a stagnant system, static system, have already calculated AT is equal to A naught, the initial concentration. Yeah. In the static reactions, we have derived the equation like this. The amount left at the time T is equal to the concentration at A, initial concentration E power minus KT. Compare these two equations. The T, the time of variation, is equivalent to here. It is replaced by V by U. What is P by U? It's nothing but residence time already we have given. Therefore, more or less the same equation we are having. This is for the first order kinetics. For the other order kinetics, for n is greater than 1. For n is equal to 0, no general equation is available for the flow system. For n is equal to 1, no, it will not be applicable to the general equation. Therefore, we have derived a separate one. For n is greater than 1, the general equation is n divided by n minus 1 into 1 by CF. CF is the concentration at exit point power n minus 1 into Kn. Kn is the nth order rate constant, and into P by U, where V is the volume of the reactor, U is the flow rate. I'm sorry, flow rate is given once again, I have forgotten. It is not flowing rate, it is also given in terms of metric cube per second, not meter per second, metric cube per second. Therefore, in our general equation also, we have written as K and T is equal to 1 by n minus 1 into 1 by some AT power n minus 1 and so on. We have written like this, just like the general equation. For the flow system also, this is the equation we are adopting. Now, making use of this reaction, we are going to work out one problem, and then we are having our if rate, take down the problem. In a plug reactor, the concentration of the species, at the exit of the reactor, the concentration of the species at the exit of the reactor is going to be doubled. When the flow rate is doubled. What is the order of the reaction? And we will do the problem in next time. In the meanwhile, we will do another problem. In a flow technique kinetic study, take down this problem. In a flow technique kinetic study, the following data are obtained. The volume of the reactor is given by pi into 0.01 square into 0.3 m cube. What is this? It is nothing but the cone-shaped, cylinder-shaped pi r square h in பார்த்திருப்பீங்களே, அதைத்தான் இப்படி எழுதியிருக்காங்க, pi into r square 0.h meter cube. Don't be afraid of it, why they are giving like this. It is a cylindrical reactor, 0.3 m meter cube, and the flow rate U is equal to 0.01 meter cube per second. The reaction is second order. And the rate constant is 8 into 10 power 6 bm cube per mole per second. If the concentration of A, the concentration of the species அப்படின்னு சொல்லுங்க. Now A, the concentration of the species in the mixture at the entry point is 4 into 10 power minus 2 mole per dm cube. What would be the concentration? What would be concentration at the exit of the reactor? At the exit of the reactor. Okay, we are going to find out what is the equation we are using. N by n minus 1 into 1 by Cf power n minus 1 into K n into B by U. Here n is given, Cf is asked, what is the concentration on this one, and Kn is given, B is also given, and U is given. Substitute, you will get that. What is that amount? This is the concentration of the species at the exit. And therefore, you can apply this one. Already I have given one more problem for this to find out the order. I think you will easily work out for this. Now work out this within the home and the previous problem now itself. What is your answer? Previous problem, flux reactor. What is find out the constant order of the reaction? For which we are also going to use this one. This equation should be used for the reaction having order greater than 1. We should not use these for the first order kinetics. There will be separate one. This is the equation. First equation. Second word, what is given? In a plug reactor, the concentration of species at the exit of the reaction is found to be doubled. It is found to be doubled up. Therefore, it is given 2Cl into n minus 1 equal to K into n. What is given? When the flow rate is doubled, 2 into U. Why I have put the flow rate is 2 times increase. This is equation. Now substitute. Divide one equation by another equation. Let us divide as such. N by n, this and this cancel, kn cancel, v cancel, u cancel. And finally you would be left out with C of n minus 1 by C by 2C of n minus 1 equal to, here the balance is 1 divided by 1 by 2. Now you can easily find out this equation can be changed is 2C of n minus 1 by C of n minus 1 equal to 2. And this and the C of CF cancel, and 2 of n minus 1 equal to 2. Therefore, n minus 1 is equal to 1. Is equal to, it's a second order kinetics. Thus, you can easily work out this. Okay, with this, stop this session.